All right, hello everybody. As she mentioned, my name is Kaylyn Gibilterra, and I work at Capital One. I'm often doing APIs and services and writing things for future products, but I've found over the last year I've started writing algorithms for fun, which I think for a lot of people is strange. It particularly feels strange for me because in college, algorithms was a class that I absolutely hated. I had a very arguably brilliant professor, literally a professor with a multiplication algorithm named after him. Not quite fast enough that anybody uses it, but worthy of a name. But when he would teach, he would often use all of these phrases and go through all of these proofs that felt very foreign and sort of talk in a way that was like, of course, this should be obvious. This is how you do these things, which was very easy for me to be like, all right, this is not for me. I basically learned enough to pass my interviews and moved on with my life. That actually changed when I started trying it out over the past year in Go. What I was really surprised about was even if the algorithms were described in C or Java, I could still figure out how to do it in Go, and I felt like I understood it way better than I had with instruction. So I'm going to explain to you why that is, show you how to do it with binary search trees, but before we dive too far into it, we should go into why exactly learning algorithms is so awful. And I probably shouldn't blame one source, but I'm going to. If you have seen this textbook, it is called The Introduction to Algorithms. It came out in 1989 and is sort of considered like the gospel of algorithms books. And to their credit, there hadn't been a great book before that period in time, but it was written by a bunch of professors, and you can see when you're going through the book that they wrote it for their academic friends. Some examples of this. If you're going through the page, you see lots of terms of things that were referenced earlier in the book. So you need to know things like what satellite data is, what is a linked list, how do you go through traversing trees. And if you haven't read every single page of the book and probably been taking notes on it, you might not actually be able to remember what all those are. On top of it, if you're anything like me, the first thing I look for is something that looks like code. On this page, this isn't binary search tree code. This is actually code that's explaining to you how to walk through a tree, and it spends most of the page discussing all of the ways that you could go through it. So there's in-order search, pre-order, post-order, and I kind of look at that and I'm like, wait a second, but what is the actual binary search tree? The worst offense, though, is the entire bottom quarter of this page is a theorem and a proof. I'm sure they did this well-intentioned. I think a lot of academics, when they're telling you something, they feel like, I need to prove to you why this is true. If I don't prove this to you, you're absolutely never going to trust me. The irony here is that this book is supposed to be an introduction, so it's for a lot of beginners that probably just will trust you. I don't need to know all of the proofs and all of the exact details for why this algorithm is correct, but they provide that. To their credit, they do have this two-sentence area over here that does actually explain what a binary search tree algorithm is. It just does it in this sentence format, and they format it as a binary search tree property, which again sort of is confusing terminology if you're somebody coming at this new. So what I kind of learned when looking through these books is, first of all, academic textbook authors are generally not great teachers. I don't know what that correlation is, but for whatever reason, the best teachers seem to not write enough books. And unfortunately, because of that, most people tend to copy that model. So even if you don't read from a book to learn your algorithms, you might go online and you're going to find a lot of the same format. They're going to be referencing all these things that they think you probably already know before looking at a binary search tree. And the reality is most of this required knowledge is absolutely not needed at all. So the rest of this talk is going to be walking through what a binary search tree is, and this will be hopefully great for you if you are new to Go. Or if you're new to algorithms, this will probably have a lot for you to kind of see the flow and see how it all works together. If you aren't new to either of those things, maybe you've been writing a lot of Go, and you do algorithms, hopefully this will be a nice refresher and also something that you can pass on to other people, because for a lot of people, they would love to know more about these. But there is only one thing that I think you need to know how to do before understanding all of this talk. And this is what I would call the guess the number game. There isn't a formal name for this, but probably a lot of you played it when you were children, and it's essentially around the time you learned to count, you started asking your friends like, hey, I have a number between 1 and 100, I bet you can't guess what it is. And your friends diligently threw out a number like 57. Now, they were generally wrong, because that's a wide array of numbers, but you were going to give them hints, so you would say things like, no, it's lower than 57. So our gopher here, gopher 2 now would know that it's somewhere between 1 and 57. It's not between 1 and 100 anymore. And you can keep playing this game. So they guess 32, you say it's higher, you continue going on, 48, lower, 39, and eventually you are going to find your answer. What you are doing here, these numbers that the gopher 2 has thrown out are literally the numbers that would go in a binary search algorithm. This essentially is what you do. You throw out a number and you get an answer of, is the answer I'm looking for higher or lower? And you go through checking each piece of this as you go through your algorithm. So if it's higher, you're going to guess above 32. If it's lower, you go to 39, and then you go to 35. This is essentially binary search. If you can follow along with this guessing game, you can basically follow along with all of binary search trees. Hopefully that's somewhat refreshing. Now, they don't all look exactly like this. This is, of course, just the path you would follow in binary search. Most look something more like this, where you have a bunch of different nodes that you could go through and you're going to check, is there a path that I can follow here, or is there not? But it still ends up being essentially the same binary search guessing game algorithm. All right, so I dived in pretty quickly, but there's a lot more than just this binary search guessing game. So I wanted to take a step back and define exactly what a binary search tree is. So the first aspect of it is that each node is going to contain one unique key. You use this so that you can actually do comparisons. It's often an integer, it might be something like a string, but you have to be able to ask the question, does this value come before or after what I have in the key? Each node is also going to have at most 2 children below it, so it can only point to 2 other data points. This is because you're asking this question again, is it higher or lower? If we had more than 2 data points, you would have a spectrum of answers, and it's like, well, it's higher than this one, but not quite that high, which wouldn't work. So you do have only up to 2 options. If the key is greater than the node that you are looking at right now, you are going to go to the right and traverse that angle. If it is less than, you are going to go to the left. And the last point is that you cannot duplicate keys. If you are duplicating keys, you then have to add in more code that's essentially checking, hey, which one of these values of 50 do I want, which is a little painful and not worth your time. All right, so we are going to go back to the picture of the actual tree. There are 3 major functions that you do with a binary search tree. You search, and you can insert, and you delete. And binary search trees are really fast at all of these things. This is why they are so popular. The search aspect is very identical to our guessing game, so I'm going to run through it pretty quickly. But essentially what you do is you go less than, so 32, 39 is greater than 32, so we move to the right, which is 48. And we continue going on until we get to 39. Now we have found that 39 equals 39. Perfect, we know now what we are looking for. A huge point to bring up is that everything on the right of the node that you are looking at is going to be greater than the value you are at. So you can see here all of the green values are bigger than the 57. On the left, all of the values are less than. This holds true for your very first root node as well as any other node that you are going to look at. So if we started looking at this 32, what you would see is, again, everything to the right is greater than and everything to the left is less than. If you changed one of these values, say you changed 35 to 31, this theorem no longer would hold true. Because if you look at this, you would go through 32 and be searching along and all of a sudden find a number that is less than 32, which would break this whole algorithm. So, knowing that this is the fundamentals of your binary search tree, this is the code that we would start writing. The fundamental structure that we are going to use is a struct, and if you are new to structs, they are essentially a collection of fields. You can put any amounts of fields in there, any sorts of data that you want, but the 3 that you absolutely need are the key, which again I mentioned is something that you can compare to other keys, and then the left and right. So is this the left node or is it the right node that I want to go to, which is greater than or less than? This is considered a recursive structure. If the word recursion freaks you out, don't really worry about it too much, but essentially what you're doing is you're saying, hey, I want to go to that next piece of data that is greater than or less than on either side. When you want to define this data, you can do it using a struct literal. So this is a struct literal here. It's creating a node, and it has a value of a key. You might be wondering where the other data points are, because there's key, there's left, there's right. You can list all of those if you want to. So right here we have key named, then left, then right. You do not need to list all of those names if you have the actual named fields in there. You can also do it without the name. So if you wanted to just say, hey, 6 nil nil, you can do that as well. In this case, you need to be concerned with the order that you're instantiating it in, because it will do it down the line of your struct. After you have your struct declared, you can then start referencing it, and you can reference your struct fields using dot notation like this. Okay, so this is the structure that we have. Now we can actually start looking at the algorithms of how we would go about searching this tree. The major first step that we have here is that we are checking if we get to a nil node. So if at any point while we are traversing our tree, we find a nil value, we now know that the key we are looking for does not exist inside of our binary search tree. If we haven't found that yet, though, we are still looking at valid nodes, we can start comparing and doing our kind of guessing game to figure out which direction to go to. So if the key we are looking for is greater than the node we are at, we are going to move to the right. If it is less than, we will move to the left. And if it is neither of those cases, so if it is neither greater than nor less than, we know that it is actually equal to the key we are searching for, at which point we can return true. We have found the thing that we are looking for. I will walk through this for people who might be a little bit more visual. This is essentially what we saw at the very end of our last example. If we were looking for the key value of 39, we would get to the node 48, and we would look to the left, say, hey, it's going to be less than. Move over to the left. We now have a node key and an actual key that equal the same thing. We have found this variable. Conversely, if we were, say, looking for 49, what would actually end up happening is we are going to move to the right. We're going to say 49 is greater than 48. The variable must be on the right side of this node. Let's look over there. When we look over there, we find that there isn't a value. And that now tells us that absolutely this value does not exist inside this binary search tree. So you end up going into this nil and returning that. Now, a little bit more complex, not just quite the guessing game, is we want to start inserting values into our binary search tree. So we want to insert the value 81. If you are looking at this picture, you can sort of see potentially where it might go, but we're going to follow it along. So we're starting with, inserting the value of 81. We are starting with 57, and 81 is greater than 57. We're following kind of the search algorithm, going to the right again because it's greater than 78, and now we hit 85. And we say, okay, 81 is less than 85, I should be moving towards the left. When we look over there, there's nothing that exists there, so we can now insert our gopher at that spot, and we have put the 81 in there. Now we can start looking at this code as well. So in here, we are doing essentially the same sort of check. If it's greater than, we're going to move to the right. But before we move to the right, we're going to check to see if it's an empty node in there. And if it is actually empty, we can just insert it and get out of this function. If it's not empty, we're going to recursively keep searching and go, okay, it's greater than this. Let's see what happens next. And the exact same thing happens on the left. We are going to recursively look through it. But before we run the recursive function, we always do the check, is this a nil node? And then put the value in there if it is. A comment that I wanted to make here, particularly if you're newer to Go, so you see at the top this function call. And so we have function and then n with a pointer to a node in there. If you haven't done a lot with receivers, you might be wondering what's going on at that point. So this is a pointer receiver, and essentially what it's saying is it's going to take a node, and you can only do this insert function on nodes. But not only can you only do it on nodes, it's also allowing you to manipulate that node as you run through this function. So if you change the key inside this function, it will be changed when you reference it later on. So that's essentially what we call a pointer receiver in this function. All right, so we are now at the last example that we are going to be walking through with binary search trees. So this is delete. It gets a little bit more complicated, kind of a bit more fun. There's a bit more to track and watch as you're going through the example. So we are going to be deleting 78. So we're at 57. We know that 78 is greater than 57. Move to the right. It's the very next item. We have found it, and we know that we now want to delete it. So the first thing that we're going to do is check to the left. Is there anything to the left of this gopher? And we find that there isn't one. This is a great use case. This is a happier delete function. And what that means is we are now able to essentially just draw a line from 57 to 85. We are just going to move on to that next node. We no longer need to care about 78. We don't have to worry about moving data around. It is just able to be passed over to go to 85. So then we'll look at the code to start here, and we'll go through some of the more in-depth examples after this. So here's the delete code. The first thing that you're going to do is search for the node that you want to delete. This is the same that we did in the last two examples. Greater than, go to the right. Less than, go to the left. Once it is found, you do this check. You say, hey, is the left empty or the right is empty? If either of those nodes are empty, you're in a pretty good spot. You're just going to point to the opposite node. This is okay. If both nodes are empty, that's perfectly fine. You're going to point to a nil, and that will effectively delete that entire subtree. But you're pretty much okay as long as one of those nodes are empty. If there are two children underneath, though, this is when you kind of have to think about what's going to happen. Because if there are two children, you now need to not just say, oh, I'll pick one randomly. You need to find the next highest number that should go in that position so that your tree stays correct. And how do you go about doing that? Well, the first thing that you do is you're going to find the minimum value from the right subtree. So of all of the higher than numbers that are on the right, you're going to find the least value among them. It's a little simpler if you just look at the picture. Min and max are actually quite simple functions. It's very nice. When you start at a node, any node, you essentially just move to the left forever. You move and move and move to the left, and when you find a nil, you have now found the lowest value of that subtree guaranteed. Same for the max. If you move to the right for over and over and over, eventually you get to the highest number. You can see here if you move down, you get to a 96, and there is still a child node under there, but it's going to the left, so it's a 90, which ends up being less than 96. So you will always end up with kind of this min or max. So this is the code for min and max. It's kind of fun to look at, but essentially you're just checking for that. Is the left node nil? Is the right node nil? Once that happens, you can escape out. So now we are going to go back to our last example. So we had the 57. We were going to delete 78. We went through and we saw, all right, this is greater than. We're going to go through and check if the left is nil. We find that that is true as well. And effectively, we can delete 78. That's great. What do we now do if we wanted to delete this 85? You can kind of see in the bottom corner here, it's pointing to two children. So this is a different use case. If we highlight this 85, we go through and we do this check and we say, hey, is the left side nil or the right side nil? No, both of them are true, so where do we go next? We go and we find the minimum value of the right subtree. So we go first to 96 and we say, hey, is 96 the minimum value of the right subtree? It is not. 90 is in fact the minimum value, so we are going to return that from min. Now what we do here is we don't just kind of swap them around. We actually only update the key of the 85 node. We're going to keep the parent children as they are, or the children nodes as they are, update the 90 there, just update that key. And if we didn't do that, say for example, we just decided to swap the nodes, this would completely break your tree. Because the 85 node is referencing those nodes on the left and the right, so you can't just delete that node. Otherwise, you will have no references to get back to that in the future, and you'll kind of have two separate subtrees working on. So you'll update the key, and then you redo the code again. So you recursively start deleting, but now you've updated the parameters to be starting at 90, the node with 96, and you're searching for 90. So you go back through, find the 90, and you can delete that. And you're guaranteed that this new 90 you're deleting will, in fact, be able to be deleted because you know it's the lowest number of the greater side on the right. All right. So this is the basic code for the major functions of binary search tree for insert, search, and delete. There's a couple more things that we can add in here that are a lot of fun. So when I started writing algorithms, I was figuring it out in Go. It was more friendly. I really liked that. But it was actually when I got to testing that I started to actually have some fun. And this is because testing is pretty difficult in a lot of other languages. Even when you're working with Python or C, you often end up having to kind of do timers to figure out how long things are running and to see if it's making a difference if you're switching between arrays and maps or things like that. Fortunately, in Go, you don't have to do that, which makes it actually worthwhile to test, in my opinion. So what we have here is an example of testing your search function. So what's going on here is we are creating the test tree. So this has a value of 6 in the root, and then you see we actually continue creating another node. So we're making a node on the left that says 3. We start running through tests, and you might be wondering what those tests actually are. Where do they come from? So in this corner here, this is actually the most fun thing for me, is this is all the code that you need to get tests up and running for Go. So you have to import just one library, just the testing library, and then after that, you can start doing all of these functions. So below the testing library, I have what's called a test table. You can make as many of these as you want. You can have all sorts of different variables in there that you want to check, but the minimum that you tend to have is the input and output. So in this search function, what we will be checking is, hey, I'm going to pass in a 6, and I want to know if there's a 6 inside or not. We'll then pass in a 16, and I would expect that there should not be a 16 inside of that tree because we never inserted one. So you can kind of run through and see just in that code how you're going to do those tests. Another comment that I wanted to make. So after we do this for loop, actually in the for loop, you can see right there, there's for I test equals range tests. If you are unfamiliar with Go, this is kind of a nice function that you have. This is the equivalent of saying for I equals 0, I is less than the length of tests, and then I plus plus. Whereas then in the for loop, you would have to reference test with annotating of I. In this case, you can just start using the test inside your for loop, which is nice to have. But the other point I wanted to mention is that line underneath where I say result is equal to tree.search test input. You can do this in this way, and essentially what you're doing is you have this result variable that lives for the entirety of all of these for loops. Well, for each for loop iteration. But you can also do this thing in Go where you are instantiating the result variable only with inside that if statement. This is slightly clever because you don't have to worry about if you use the same variable in multiple locations, but you can still have it to print out for errors. So this is really nice in testing. You can create your result, then you can set it to something, you can check if it equals the output you expect, and then you can print it out at the end, but it only lives with inside of that test iteration. The last thing to call is this is all you have to do to run this test, is you write go test and it will run for you, and it's really nice and it will tell you if it's passing and print out these error message for you in each iteration that you have. There's a bit more though. This is probably the most relevant piece for learning about algorithms. You can actually do very simple benchmarking in Go. So this is an example of it, and this is all of the code that you would need. So in it, you're going to include b testing.b. What that gives you is a for loop that you can use where you do this for I equals 0, I is less than b.n, I plus plus. What this b.n variable is, I was a little confused the first time I started writing it, like, how does this happen? What does this mean? That is going to run the function that you have inside that for loop over and over and over again until eventually you're getting a stable speed, a stable response time for that function. This is super phenomenal for testing, and you actually only have to run this little command to get them going. When you run this, you get an output that looks something like this. And the major thing that you're concerned with in here is this line here. This line here tells you basically the speed of the function that you have. So in this case, it was 2.84 nanoseconds. You can then start testing things like, hey, what if I put a larger tree in there that had a lot more nodes inside of it and we had to search longer for that 6? You can start seeing how the speed would change and decrease over time. I've found this very helpful for really understanding the difference in speed between like when I might be using a large map and a large struct, and if I can convert it into using just an array or a slice, you can see the performance differences, and it's really nice to just get that practical feedback confirming the things that you read about online. So this is like the fun things that you get out of Go when doing algorithms. All right, so I wanted to reiterate some of the facts around binary search trees. We talked about this a few times, so I'm just going to show it really quickly, but essentially you need unique nodes, and you're checking if things are greater than or less than. I'm reiterating this because the last thing we're going to be walking through is a lot of binary search tree terminologies. So if you were to go about your day and decide, hey, I want to start looking at all of these binary search trees and learning them for fun on my own, there's a lot of things that you'll start to encounter, and these are sort of the things that were in the academic textbook and might be online, and they just sort of throw these terms out all over the place, but they're helpful to kind of have a grasp over before you start. So the first one I wanted to bring up is tree height. So tree height is essentially the longest path you have from the root of your tree down to one of the children. So in this example, we have a tree height of 5. That is the longest path that it would take to get down to that 43. And this helps you determine how fast your algorithm is. You're always looking for the longest answer that you would find when going through this tree, and so finding that gives you the tree height. You can do this, though, not just from the root. So you might be curious, what is the node depth? So say I'm searching for 48. I am going to find that the node depth of 48 is 2. Going from the tree down to 48 is 2, which would be a lot faster than searching for that 43. One of the final concepts to bring up is what is a full binary tree? People reference this a lot. So what a full binary tree means is that every single node has 0 or 2 children. So in here you can see that like 57 has 2 children, 24 has 0, 48 has 2. You see that they all have 2 or 0. None of them just point to one thing. This will come in handy in a couple of terms. There's another concept, though, about complete trees, kind of similar. And essentially what it means is that if you were to look at every single row, it's completely full. Now, it doesn't have to be full for every single row. The last one can actually have some extra nodes on there, but they have to go from left to right. And the reason that there's all this terminology is because that there is actually a problem with binary search trees if you're not careful. The big problem that you have is that you would have an unbalanced tree. So in this case, we have a tree height of 3. And that's great, that's fantastic. It's very rare that we're going to get different speeds for the different answers we have because they're mostly flat. If we start inserting more values, you're going to insert 47. Now we have a tree height of 4. Still not much of a problem, but you can keep doing this. So you go down to 46, and then 45, and then 44, and now all of a sudden you have a tree height of 7 for that one path. But the rest of the nodes that you're going to look for will return really quickly. And this actually can very easily happen if your tree just becomes more and more unbalanced. And so this will be an issue where if certain searches were taking a really long time to return and some are coming quickly, it could be because you have an unbalanced tree. What you would want to do is essentially make it more of a full tree, have this more balanced view. So all of the nodes in here, these are the same nodes from before, but they all have only 2 or 0 children that point to them. And this makes it much faster. There's only a tree height of 4. It's much shorter than the tree height of 7, the time that you would be using in the past. So there is a ton that you can learn about binary search trees. There's so many fun examples. They really get more involved from here on. And I would absolutely love to talk to anybody who might be interested in them in the future. I have my contact here. If you would love to talk about it after, I'll be standing probably in the corner or right outside in the back. But I would love to talk about these trees or any sorts of algorithms. Or if you just have questions that you may not want to ask in a public area, I would love to talk through those as well, too. Thank you so much.